Okay, so now we're going to look at the image that's formed by an extended object reflecting off of a spherical mirror. So let me draw the situation again. I'll do my best to draw spherical mirror. And we have our optical axis here, which defines our vertex here, and our center of curvature somewhere here. And this time, we want to consider not just a point, but an extended object. So we'll call this P, point down here, and this point up here we're going to call Q, and we're going to call this height of the arrow, we're going to call it Y. Alright, so an extended object, and like we mentioned before, we can figure out what the magnification and image distance of the image is just by considering the rays that are coming from the tip, because these, we know what they do, and the tip gives us the information of where the end of the arrow is, so that defines the start and the end of the arrow, and that tells us the height of the image, if it's distorted or what's going on with it and where it is. So let's do just that. So we are going to do two example rays. One of them is going to go right through the center of curvature, and because it goes right through the center of curvature, that means that it's approaching right at that normal, and so it's going to reflect right back at itself, like that, right? Then we're going to do another ray that goes right to the vertex. Right to the vertex. So rays are coming out in all angles, but we're just considering the ones that are most useful to figure out what's going on. And at the end of all this, I'm going to give you a nice little summary of types of rays to draw for different scenarios in order to determine what we're doing. So this, I'm going to try to draw the best that I can. The reflection here. This is going to be an angle of incidence, and this is going to be that same angle of reflection. So therefore, evidently, they intersect right about here, if my drawing is worth anything. And so that means that the bottom of the arrow is obviously still on that optical axis. And I say obviously just because the ray is going to be emanating from the bottom of the arrow, hit exactly on that normal to the surface of the optical of the mirror, and then reflect right back, right? And so the bottom of the arrow is going to also be on the optical axis. So that's kind of an implicit understanding. And so the arrow tip is really what we're trying to figure out. Well, so look at this. The arrow tip is below the optical axis. So the image has been flipped. And also, I will say to you that this is not just a result of my poor geometric drawing. This one's actually pretty good. The image, y prime, the image size here, is smaller than y. So there's some magnification going on here, right? There's some magnification going on here. So we have an object distance, just the same as we've considered before. Object distance, oops. This is what I meant to do. From the arrow object to the vertex, that's S. And we have some image distance, which is from the vertex to the image arrow, which might be a little further than that. There, we'll go with that. That's S prime. And we also have radius of curvature, which is from C to the vertex. That is the radius. Alright. So, the arrows are different heights. So that means when we do M is equal to y prime over y, we don't get 1, right? So we have some magnification happening here. but Joel, the arrow is smaller, and you said that it was being magnified just now. Yeah, well, magnification refers to both images that are getting bigger and smaller than their corresponding objects. The magnification in this case would simply be less than 1, right? So I want you to notice two triangles again. So the triangles P, Q, V. I'll do it in orange again, or I guess I did it in green before. P, Q, V. This triangle. And also the triangle P prime, Q prime. Oh yeah, I didn't write that. So this is P prime and this is Q prime. P prime, Q prime, V. They are similar triangles. This means that we can relate their dimensions. So for those two triangles, we can say, I'll write it up here, y over s is equal to negative y prime over s prime. The negative sign is needed because the optical axis defines y equals 0. So anything up here is positive y, and anything down there is negative y. So up is positive, down is negative. Makes sense. So therefore, we have this relation. So we can go further here and say negative s prime over s. And that is our lateral magnification. For a spherical mirror. Spherical. I think I did a capital M before, and I meant to do a lowercase m way back here somewhere. Yeah. Lowercase m. Sometimes those details matter because they can confuse stuff. So if m is positive, then the image is what's said to be erect, right? Positive m equals erect image. It just means not inverted from the object. If m is negative, then the image is, like I just said, inverted. And if m is greater than 1, then the image, I'll just say bigger. And if m is less than 1, then the image is smaller than the object. All right. So recall that for a plane mirror, we had that s, the object distance, was equal to negative s prime, the image distance, right? That was this up here. This gives a magnification of 1, so no magnification, right? So there you go. So you now have the tools to determine what image is formed by a concave spherical mirror. So we've been talking about concave spherical mirrors. So long as it's a one-dimensional arrow that starts on the optical axis, you just draw two representative rays from the top arrow, one from tip to vertex and the other from tip through the center of curvature, and one from the bottom that follows the optical axis if you would like. I will leave it to you as an exercise to determine what kind of image is formed if the object arrow originates at a point between the center of curvature and the focal point. Does it form an image? Is it virtual or real? Is it erect or inverted? Is it magnified? Is it magnified smaller or larger? How about for an arrow that originates between the focal point and the vertex, right? So go ahead and try your best at investigating those cases, and if you have to, consult other resources to help you in those cases. And it helps just kind of get a picture of what the different scenarios are depending on where the object is and what kind of reflection surface you have and all of this. Next, I'm going to talk very briefly about convex mirrors, and then I'm just going to summarize the graphing of principal rays that we've talked about.